In this tutorial, we will discuss the application of neural networks on graphs. Graph neural networks have recently gained increasing popularity in both applications and research, including domains such as social networks, knowledge graphs, recommender systems, and bioinformatics. While the theory and math behind GNNs might first seem complicated, the implementation of those models is quite simple and helps in understanding the methodology. Therefore, we will discuss the implementation of basic network layers of a GNN, namely graph convolutions and attention layers. We will start by importing our standard libraries. We will use JAX and Flax in this video. Before starting the discussion of specific neural network operations on graphs, we should consider how to represent a graph. Mathematically, a graph G is defined as a tuple of a set of nodes vertices V and a set of edges links E. Each edge is a pair of two vertices and represents a connection between them. For simplicity, we assume the graph is undirected, so we do not include mirrored pairs such as 2, 1. In practical applications, vertices and edges often have specific attributes and edges can also be directed. The challenge lies in efficiently representing this diversity to facilitate matrix operations. Typically for edges, we choose between two representations, an adjacency matrix or a list of paired vertex indices. The adjacency matrix is a square matrix where each element indicates whether a pair of vertices is adjacent, meaning connected or not. In its simplest form, the entry is 1 if there is a connection from node I to node J and 0 otherwise. If the graph includes edge attributes or different types of edges, this information can also be incorporated into the matrix. While expressing a graph as a list of edges is more efficient in terms of memory and possibly computation, using an adjacency matrix is more intuitive and simpler to implement. In our implementations, we will rely on the adjacency matrix to keep the code simple. However, common libraries also use edge lists in such cases. Graph convolutional networks are similar to convolutions in images in the sense that the filter parameters are typically shared over all locations in the graph. At the same time, GCNs rely on message passing methods, which means that vertices exchange information with the neighbors and send messages to each other. Before looking at the math, we can try to visually understand how GCNs work. The first step is that each node creates a feature vector that represents the message it wants to send to all its neighbors. In the second step, the messages are sent to the neighbors so that a node receives one message per adjacent node. Here, we have visualized the two steps for our example graph. If we want to formulate that in more mathematical terms, we need to first decide how to combine all the messages a node receives. As the number of messages vary across nodes, we need an operation that works for any number. Hence, the usual way to go is to sum or take the mean. Given the previous features of nodes HL, the GCN layer is defined as WL is the weight parameters with which we transform the input features into messages HLWL. To the adjacency matrix, we add the identity matrix I so that each node sends its own message also to itself. That is, A hat is equal to A plus I. Finally, to take the average instead of summing, we calculate the matrix D hat, which is a diagonal matrix with D, I, denoting the number of neighbors node I has. Sigma represents an arbitrary activation function and not necessarily the sigmoid. Usually a ReLU-based activation function is used in GNNs. When implementing the GCN layer in JAX Flax, we can take advantage of the flexible operations on tensors. Instead of defining a matrix, we can simply divide the summed messages by the number of neighbors afterward. Additionally, we replace the weight matrix with a linear layer, which additionally allows us to add a bias. Written as a Flax module, the GCN layer is defined like. To further understand the GCN layer, we can apply it to our example graph above. First, let's specify some node features and the adjacency matrix with added self-connections. Next, let's apply a GCN layer to it. For simplicity, we initialize the linear weight matrix as an identity matrix so that the input features are equal to the messages. This makes it easier for us to verify the message passing operation. As we can see, the first node's output values are the average of itself and the second node. Similarly, we can verify all other nodes. However, in a GNN, we would also want to allow feature exchange between nodes beyond its neighbors. This can be achieved by applying multiple GCN layers, which gives us the final layout of a GNN. The GN can be built up by a sequence of GCN layers and non-linearities such as ReLU. However, one issue we can see from looking at the example above is that the output features for nodes 3 and 4 are the same because they have the same adjacent nodes, including itself. Therefore, GCN layers can make the network forget node-specific information if we just take a mean over all messages. Multiple possible improvements have been proposed. While the simplest option might be using residual connections, the more common approach is to either weigh the self-connections higher or define a separate weight matrix for the self-connections. As you might know, attention describes a weighted average of multiple elements with the weights dynamically computed based on an input query and elements keys. This concept can be similarly applied to graphs. One of such is the graph attention network. Similarly to the GCN, the graph attention layer creates a message for each node using a linear weight matrix. For the attention part, it uses the message from the node itself as a query, and the messages to average as both keys and values. Note that this also includes the message to itself. The score function is implemented as a one-layer MLP which maps the query and key to a single value. HI and HJ are the original features from node I and J respectively, and represent the messages of the layer with W as weight matrix. A is the weight matrix of the MLP. Alpha ij is the final attention weight from node I to J. The calculation can be described as, we can see that without the non-linearity, the attention term with hi actually cancels itself out, resulting in the attention being independent of the node itself. Hence, we would have the same issue as the GCN of creating the same output features for nodes with the same neighbors. This is why the leaky ReLU is crucial and adds some dependency on hi to the attention. Once we obtain all attention factors, we can calculate the output features for each node by performing the weighted average. Sigma is yet another nonlinearity, as in the GCN layer. Visually, we can represent the full message passing in an attention layer as follows. To increase the expressiveness of the graph attention network, extension to multiple heads similar to the multi-head attention block in transformers was proposed. This results in attention layers being applied in parallel. It is visualized as 3 different colors of arrows, green, blue, and purple, that are afterward concatenated. The average is only applied for the very final prediction layer in a network. After having discussed the graph attention layer in detail, we can now implement it like this. Again, we can apply the graph attention layer on our example graph above to understand the dynamics better. As before, the input layer is initialized as an identity matrix, but we set A to be a vector of arbitrary numbers to obtain different attention values. We use 2 heads to show the parallel, independent attention mechanisms working in the layer. In this tutorial, we have seen the application of neural networks to graph structures. We looked at how a graph can be represented as adjacency matrix or edge list, and discussed the implementation of common graph layers, GCN, and graph attention network. The implementations showed the practical side of the layers, which is often easier than the theory.